Hello, everybody. Welcome back to day two. And again, on behalf of the entire team at Q2B, we'd like to welcome all of you here. The next 2 days are going to be very, very busy. And just to kick things off, I want to start talking for just a couple of minutes about the future of quantum computing. And I'll do that as soon as this clicker starts to work. Hopefully they can hear me back there. There we go. No. Guys, can you reset to the very first slide, please? Stealing all my thunder here. It's early. Okay. Anyway, let's talk about the future of quantum computing briefly. So none of us in this room know where quantum computing is going to be in 1 year, let alone in the next 5 to 10 years. But a lot of us in this room, when we're confronted with something new and a little bit unknown, we resort to pattern matching. And I'd like to do that now. And the reference point that I think is appropriate to use for quantum computing is our next door neighbor. It's classical computing. So I'd like to take you on a little journey now where we look at some of the key historic milestones in classical computing, map them over to quantum, and then make some inferences about what may be in the future for our industry. And the first thing I want to do to set the stage for that is to take you all back in time about 400 years. In the 17th century, Gottfried Leibniz had a vision. And let's keep in mind, just about everything important that's ever been built has started as a vision in some person's mind. And for the entire computing industry, that person was Leibniz. So in the second half of the 17th century, Leibniz put down on paper the design for a mechanical computing machine. And by the way, many of the elements that he documented still appear in today's digital computers. Now, the machine that Leibniz envisioned actually got built in his lifetime, and it actually worked. Unfortunately, the electronics industry had not yet been created, and so we'd have to wait a couple hundred more years for those machines to appear. But anyway, we in the quantum computing community are lucky that we also had a similar visionary, and that person was Richard Feynman. In 1982, Feynman published a paper where he proposed a computer that operated by harnessing quantum mechanical phenomena. And he further stated that such a machine would be well suited to solve problems in physical sciences, in our physical universe. But importantly for all of us in this room, he also added something. He said that such a computer can also be used to solve classical problems. And this, in 1982, is something that very likely excited the computer science community who thought, aha, someday, perhaps soon, I'll have a new compute resource to work with. So let's go back into the classical realm, fast forward about 300 odd years. At the start of the 20th century, something was starting to get built, and that was the fundamental building block of every digital computer, a logic gate or a switch. And the first electronic switches, as we all know, were vacuum tubes, and the first ones were starting to be manufactured in 1907. Now, fast forward about 40 years to 1947, and a group of researchers at Bell Labs did something that was seminal for the computing industry. They developed the first solid-state transistor. Let's listen for just a couple of seconds to what two of those inventors had to say about this.
At Bell Labs on December 16, 1947, John Bardeen and Walter Brattain invented the point contact transistor. It sparked an electronics revolution.
We knew we were onto something very important, and transistors would have many applications.
You may be able to get music with a flick of your wrist from the so-called Dick Tracy radio.
Fascinating. All right, that was a seminal moment in classical computing. 13 short years after Feynman's paper, in 1995, a group of researchers at the University of Colorado achieved that same milestone for quantum computing. And in this case, these researchers contained two ions in a trap and got those ions to perform logical operations, gate operations. This was huge. Now, I don't have a video chronicling that event, and I don't need to. if you look to the far left-hand side of that photo, you'll see someone in a green and white sweater. And you may be saying to yourself, you know, that person looks somewhat like a younger version of Chris Monroe. And in fact, you're exactly right. That is a younger version of Chris Monroe. He's now a co-founder of IonQ. And Chris and many other leading researchers are in our midst. They're doing all of these they're having all these breakthroughs now, and we're part of the community. So we're very fortunate to enjoy that. Now, let's move back to milestone 3 in classical computing. And this is where things really get interesting for the people in this room. It's the commercialization. So in 1968, a group of 8 scientists from Fairchild Semiconductor moved across to set up Intel Corporation. And 2 of those co-founders, Robert Noyce and Gordon Moore, drafted this document on the left-hand side of the screen. This is the entire business plan for Intel's business. There were no financial projections or market forecasts or anything like this. And on the back of this single sheet of paper, Arthur Rock raised $2.5 million to capitalize Intel. This was interesting, and it took 3 short years later for that business to produce the first microprocessor. This is the Intel 4004. It had 2,300 transistors and a 4-bit CPU. Now, I want to take an exploded view of just part of that business plan to make a point that I think is important for quantum computing. It's routinely said about quantum computing that this is a technology that is a solution looking for a problem. We'll talk about that a bit later. I don't think that's true. But it certainly was true in the case of Intel in 1968, and evidence of that is contained all over this short business plan. First of all, when the founders of Intel started talking about what products they were going to produce, this was really speculative. They talked about diodes and field effect devices. Now, they happened to mention integrated circuits, but that was kind of like buried in the rest of the rubble. As a matter of fact, Intel's first product were memory chips, and I think the first batches were sold to Honeywell for them to put into their computers at that time. If we move further to the end uses, another part of a business plan, this was also, it's very apparent, nothing against the founders of Intel, very speculative. This was 1968. It was in the middle of the Vietnam War. And so understandably, the use cases that were very visible and present to them were things like radar systems, guidance systems, control systems. And in fact, they just happened to mention in that paragraph, in passing, a field that really didn't even have revenue behind it yet, and that is data processing. Of course, we all know how that fortunately worked out. That turned to be the killer application. And then finally, and this is somewhat humorous, these are very responsible people that are ambitious, and here's where their ambition led them. When they talked about the geographic distribution of their future customer base, they really leaned forward and speculated that some of their products might be sold outside of the state of California. Like truly fascinating. So let's listen very briefly to a little bit of talk about the thing that allowed that industry to really take off.
1965, Gordon Moore is the chief scientist at Fairchild. He's asked to write an article for an electronics magazine. He sits down with a sheet of graph paper. It's only like the 4th or 5th generation of memory chips. And he plots out those 4 generations in terms of capacity. And he realizes they're already going off the top of the page. So he gets some logarithmic paper and he plots it again, and he gets a straight line.
I made a prediction for 10 years, 1,000-fold increase in complexity. That was a wild extrapolation of very little data.
One of my colleagues dubbed this Moore's Law.
All right, true heroes. Now, let's move back to the quantum side, and I want to explain why I think in this layer of the technology stack, I think the deck is really stacked in favor of quantum computing, and we're in a much better place now than these gentlemen were in 1968. This slide, by the way, was put together by our friends at Evercore with some tweaking from us. what it depicts is all 40, over 40 hardware startups, or startups and large cap companies that are building large scale quantum computers. That is a lot of shots on goal. Compare that to 1968 in the semiconductor industry, when we had Intel, Fairchild Semiconductor, Texas Instruments, and a couple of others. But that was quite a fragile industry back then. Importantly, when you look at this, what this slide does is cluster these hardware programs into technology approaches, or the qubit matter system that each of these approaches used. And conveniently, these approaches are really orthogonal to each other. So there's not a single point of technical failure in our system. It's not like it was sort of in 1968, where researchers in that industry were saying, well, we really need to make silicon work, because if it doesn't, well, we got to give germanium a shot, and that looks a little dicey. There's a lot of different technologies here that are being explored. Secondly, what we enjoy is a huge amount of risk capital that's being put to work to accelerate technology development. This year alone, there will be $3 billion from the public and private equity markets flowing into quantum computing. And on top of that, and this is very important, national governments have, over the past couple years, seized on the importance of quantum technologies and are putting together very substantial programs that will be providing a lot of funding into these programs over the coming years. All of that didn't exist in 1968. It's not like President Nixon back then said, we need to mobilize the semiconductor industry, we need to win here. We have all of that on our side. This last point, though, is very important, I think. I think it's wrong to think about quantum computing hardware as being a brand new technology that is a sister to classical computing. I think it's just an extension. And I think the evidence of that is very clear. Look at the supply chain for classical computing. It's been developed over the last half century to support the semiconductor industry. That same supply chain that's very evolved and mature is now just being tuned and pointed at quantum computing. So all of these enabling technologies like cryogenics, semiconductors, superconductors, electronic controls, all of these things have been matured, photonics, lasers, all of these things have been matured over the last half century and are being brought to bear in quantum computing. Next milestone is software. The software part of the computing stack is just as important as the hardware side, so I just want to take a minute to talk about how that evolved in the classical realm. So right after the American Civil War, okay, it wasn't that long ago, in the 1950s, IBM started producing mainframe computers. And there needed to be a bridge between compute hardware and the user community. And that first bridge was Fortran, kind of the first high-level programming language. And it was really responsible for some degree of proliferation to happen in the usage of quantum computing. That paradigm remained in place for about 20 years until some of that processing power migrated onto our desktops. At that time, we had, for the first time, not just programming languages, we had full-scale applications. Unexpectedly, the first killer application was an electronic spreadsheet. It was VisiCalc, which begat Lotus 1-2-3, which begat Excel. But we had this whole host of applications that started to be developed. That sustained us for another 15 to 20 years when some of that processing power from our desktop migrated up to the cloud, and we had the birth of two very new classes of software. First of all, we had all sorts of services that emerged. That includes all the social media giants. Again, that was very unexpected. And importantly, we had whole enterprise software companies whose business model was built by natively building code base on the cloud. The premier example of that, I think, is Mark Benioff, who founded Salesforce. And back when he did that, he was derided for thinking that you could put mission-critical software on the cloud. And of course, he proved to be right. Now, the phase that we're in now, that we're coming up to, I'll get to, was enabled by the advent of Wi-Fi networks, cell networks, satellite networks. And that is, a lot of this processing power has now migrated across to literally the 3 or 4 billion mobile devices that exist in the world. And of course, this has given rise to a lot of apps. Now, okay, so what's the point I'm trying to make in all of this? If you look back 70 years, the slice of the overall technology stack in computing that was software was quite small. Moving through the years, what's happened is that the majority of value, as measured by revenue generation and market capitalization, the majority of that in today's technology stack is software. And so I don't think that that's going to recede. I think, as Mark Andreessen said, software is eating the world. So I think this trend to be software-centric is only going to accelerate, and I think it's also going to permeate through quantum computing. But let's take a step back and look at where we are now in quantum computing software. I think where we are right now is kind of in the quantum Fortran era. If you look at what's happening, the hyperscalers led by firms like Amazon, what they're doing, 90% of the code base they're building is meant to help to drive traffic to hardware backends. So this is really helping to accelerate the usage of quantum computing. What we're also just starting to see is the emergence of a few scientific applications. This figure is extracted from a Google paper that was published on quantum scrambling, which is an experiment that was done recently, about 2 or 3 years after Google did its quantum supremacy experiment. Pure science. That's where we are now. The next stage that it seems logical that we will be able to move into is scientific applications that have some commercial relevance. So think material science and drug discovery, and think about the computational expense of calculating properties for those molecules. This, for instance, depicts one such problem. It's calculating the binding energy between a protein and a candidate molecule. This may be where the first useful commercial applications emerge. Where all of us in this room would like to get to, of course, is having purely commercial applications that can be developed that will be useful without any linkage at all to science. And of course, this is just a canonical example of a portfolio optimization problem solved on a small-scale quantum computer. Now, as with the hardware ecosystem, here's what gives us and should give us a lot of confidence in how things are developing. Again, thanks to Evercore for this slide and the next one. There are over 80 companies, these are software startups, that are capitalized with at least a seed level of funding, over 80 of them on the application layer alone. And all of these firms are doing one of two things. They're either developing algorithms or they're discovering applications with customers. Likewise, at the infrastructure layer of quantum computing, there are over 50 companies who, this is a bit of an oversimplification, but what they're either doing is quantum processing, which means they're trying to squeeze more power out of the hardware, or quantum programming, which means they're trying to make these machines more useful and accessible. So there's a ton of activity that's going on. Now, this is the final point that I want to make, and I think it's the most important. Again, looking back to 1968, the issue was there wasn't a clear and present set of problems, large-scale, high-value problems, that were posed to the semiconductor industry. I think it's just the opposite for us. On this chart are depicted a number of use cases that have been explored over the past couple of years for potential quantum computing use. And in all of these cases, there have been quantum representations of these problems developed. These problems have been mapped onto quantum algorithms. And in many of these cases, small instantiations of these problems have been run on quantum hardware. Now, the gotcha, the important gotcha, we have to be completely honest, of course, is that none of these problems, as they're running on quantum hardware through quantum resources, can do any useful work for enterprises. And for that, this is why we're all here and why this industry is mobilized. We need bigger and more powerful hardware processors. We need better algorithms. We need to pick up efficiency gains from algorithms. And this is going to require a lot of deep scientific research and work to achieve that. But again, for us, this is a present challenge. This is really what we're all shooting for. And by the way, of course, I think we all know that it's important that it's not just us who is cheering this on and saying we're making progress. The real test of success will be when a large enterprise raises its hand and says, we are using quantum processing because we're getting a performance uptick from it. Just like we use GPU clusters because we get a performance uptick from that. That's really the test. It's when enterprises will start using this embedded in their enterprise architectures. For the groups that are the first to do this, that get this done the first, they will be applauded and feted much like the people who are being driven in these vehicles up Broadway some number of years ago were. So I'm wishing you all the luck in the world on that, and thank you very much.